and here I am here to tell you about a lesson, specifically lesson 11-8, modeling data with polynomials. Very important. Let's begin. By now you should know how to figure out the degree of a polynomial formula given data. For example, here we got ourselves a little table, 1, 2, 3, 4, 5, 6, 7, along with its results. In order to figure out the degree, we'll first minus the right from left. So for example, negative 1540 minus negative 486, then there just be some sort of result. And you just basically do that for the same thing. Then you continue on until you get a very close. You finally get yourself a repeating integer. This will be your degree. However many degrees it takes. But can the coefficient be found in the set of data given that the formula exists? And can this be done with even higher degree polynomials? Let's find out. Using example 1. In the land of Connecticut, it was deemed that all cities built must be joined by every other city directly by a straight road. When the land was first developed, there was only 3 cities, and only 3 roads were needed. After a few years, there were more cities, and the government found itself having to build more and more roads. This shows you a table along with a diagram showing a triangle, meaning there's only 3 cities, then a square, meaning there's only 4 cities. Then it goes on and on, until it gets very confusing. This depends whether there was a polynomial formula relating R, the number of roads needed, with X, the number of cities built. Does such a formula exist? If so, find the formula. We shall do so. Firstly, use finite differences to discover the degree of the polynomials. As you can see here, I developed a very lovely table showing this. You'll see that the number of cities is X, which will be on top, and the number of roads, which is R. First, we'll discover the differences. As you can see here, we'll first minus stuff like, for example, 6 minus 3 equals 3. 10 minus 6, 4, and so on. And then you get the first difference. Because they're all uneven, this would mean that this is not it. So then you do it again. 4 minus 3, 5 minus 4, etc. Until finally, you actually get a repeating integer, which is on the second difference. Because it's on the second difference, the degree is 2, quadratic. Which would basically mean that the formula that we'll be using is R equals ax squared plus bx plus c. So great, we found the formula. But what do we do now? Now, we substitute the formula in the second step, the data used in the example. For this, we use the pairs 3, 3, 4, 6, and 5, 10. So if you substitute, I meant 3 for r, and 3 for x, then, and so on and so forth, we'll get this. A system of equations is created as a result. As you can see here, the y value is has replaced r, and the x value has replaced so on and so forth. Then thirdly, in the final step, we solve the system. You use either linear combinations or matrices as an example. I rather use matrices, as they can be easily solved by using a free online calculator. At first, we'll have our thing here. You see, it just overlays. And remember to by the power of 1, negative 1. This is important because then we multiply it by the x value. And then finally we get our results. We get 0.5, 0.5, and 0. This means the solution is 0.5x squared plus 0.5x. So congratulations! We managed to figure out how to find the coefficients of a polynomial using data. But could we find out if you find polynomials with degrees larger than 2, like 5, or maybe even 3? We can find out by using example 2, as shown here. We also have a lovely table here by using n as a number like 6 by 6, 4 by 6, or 4 by 4, and etc. That s is the number of squares that are in there. Basically, the question is, how many squares can be there on an nxn checkerboard? Firstly, we use definitive differences to discover the degree of the polynomials. As you can see here, we got a table here with n equaling the how many times it times itself by, and s equals how many squares there are in the checkerboard. As you see here, we use the differences. We try to use differences as we see here, like 91 minus 55, 55 minus 30, etc. And we do the same thing over and over until we finally get our repeating integer. In the third difference, this will mean the degree is 3, or cubic. And result, our formula that we'll be using is ax cubed plus bx squared plus cx plus d. Now, we do the same thing as we did before by substituting the formula with the data used in this example. The pairs 430, 314, 25, and 11 will be used in the system. And if we do the same thing before, with using n as replacing the formula there, in the n as the result part, and then 30 for the rest of the x parts, then we'll find ourselves a system of equations as a result. Then you basically do the same thing again in the third part as well. You will solve the system using matrices. As we see here, we overlay it, and we power it to the -1, then we times it by the s value, and then we'll get a result. 1 over 3, 1 over 2, 1 over 6, and 0. This practically means that our solution is 1 over 3x cubed plus 0.5x squared plus 1 over 6x. That's a lot to say. And we'll check. Now, there are some limits to polynomial modeling. If you're calculating a data set and there leaves only one difference besides 2, this will mean that the formula, instead of becoming a quadratic normal one, will instead become x squared minus x plus 2 over 2, as shown there. Now then, if data points 4, 4, 7, and 5, 11 was added, the formula will still become the same, as shown before, even though there is a repeating integer. But instead, the data points 4, 8, and 5, 15 were used. There will be another difference, the third difference, and the formula will be changed into x cubed minus 3x squared plus 8x over 6. Congratulations! You have learned how to model polynomials by using data that is provided by finding the coefficients of degrees of 2 and larger. Now you get yourself a golden star because you deserve it. Bye-bye. Hello, and I am here to tell you about a lesson.